All right, welcome back to Math 160. Last week, we started to talk about probability distributions. It's really quite straightforward when you think about the big picture, right? You think about having a random variable that takes on a numerical value. And then you say, well, what's the probability of occurrence for each of these values? You create a table, and that table will literally tell you, oh, if I wanted to know the probability of this particular numerical value, I simply look at the table and see its respective probability. We did start off by saying, how do we know for certain that it's a probability distribution? Does anyone remember some of those key requirements that would ensure we had a probability distribution?
It needs to add up to 1.
Yes, in that probability distribution, when you look at those probabilities, if you added those together, they need to add up to 1 or as close to 1 as possible for total probability. That means it takes into account all possible outcomes. What's another one? Thank you, Studio Janine. What's another one? The random variable has to be
Numerical.
numerical. Okay, the random variable has to take on a numeric value. All right, keep that in mind. I want to finish looking at a couple problems where we actually use the probability distribution in a couple ways. One is finding the mean or the expected value. Remember, we have a formula for that. My hope is that you all have a sheet of paper where you're writing all the formulas down, because that's going to be really helpful to you. If you haven't started it yet, let this be your nudge in that direction. Take out a sheet of paper, write the word formulas on top, and put the formulas on this page. It's going to be really helpful to you. So let's go over to our notes. We're going to pick up where we left off on practice number 4. We have 4 males with an X-linked genetic disorder have 1 child each. The random variable X is the number of children among the 4 who inherit the X-linked genetic disorder. We want to determine the mean or the expected value for this probability distribution and explain what it means. As a reminder, we have a formula for calculating the mean or expected value. I'm going to write that again, and I'm going to try to squeeze it in here so that it doesn't take up too much room. So to find the mean or the expected value, you're going to take the product of each random variable and multiply it by the probability, by its probability, and you're going to add all of those together. Okay, so essentially you're saying 0 times 0.0625 plus 1 times 0.2500 plus 2 times, you get my drift? Perfect. So let's write out the actual formula with the values included. So our first product is the variable times its probability. Let me rewrite this like so, times its probability 0.0625 plus we move to the next value, which is 1, multiply it by its probability, move to the next one, multiply it by its probability. See, this is not bad. We're just applying the formula here. So we're moving through each of the outcomes for our random variable and multiplying by its respective probability. We're not going to overthink this. And remember, we're adding all of these products together. Perfect. Go ahead and take your calculators out. Let's punch this in and see if we get the same thing. The great thing about this is that we really can just punch in the entire expression. Just be super careful as you do this. Decimals tend to contribute towards errors in how we punch them into our calculator. So just be super careful. Lainey, thank you for letting me know. I appreciate that.
Yeah, of course.
Awesome. When you find your mean or expected value, would you please share that with everyone? You could either send it into the chat if you are feeling like not being too vocal today. Thank you, Emma. That's perfect. That's exactly right. So our mean or expected value, when you punch this into your calculators, you should get the number 2. So then we have to describe what the heck this means. Thank you, Sudhajini. That's exactly right. What does this mean? Here's the accompanying statement. We can expect, notice that I like to use the word expect, especially when we are trying to calculate the mean or expected value. You kind of tend to use the language that is in the problem itself. We can expect that approximately 2 children, think about what we're trying to figure out, the number of children among the 4 who inherit the X-linked genetic disorder. So we're going to use that language. We can expect that approximately 2 children will have the X-linked genetic disorder among the 4 births, right? I'm using the language from the word problem as part of my answer. I'm reiterating that language. That's one thing I really want you all to focus on as we continue through this class. Sometimes when I look at your responses in the stats application, it's really, really short. 2 children, boom, done. That's not enough. I'm going to start taking credit away if you're not explaining completely and thoroughly what your statement actually means. Okay, I want you to think about being very collegiate in this experience. Whenever you read, statistical journals, if you haven't, you should just pick up one, just to like see how things are laid out, how things are typed up, how they are described. I want you to kind of put yourself in that mindset where you literally feel like you're a statistician and you're describing the result that you found. I want you to be very thorough about that, okay? Some of you are doing phenomenal, but there are some who are a little too short. Just expand on that idea a little bit. Give yourself room to just describe everything that you're seeing. Don't be so short, okay? Part B, we want to determine the probability. Now this is different because we're just looking for the probability, but specifically that at most 2 children will inherit the X-linked genetic disorder. What does that mean, at most 2? What does that mean? That phrase. How many children are we referring to? What do you think, Sam? At most 2. If somebody said at most 2 people can come in here, how many people would that be?
At most 2. Wouldn't that be 2 and everything below it?
Yes, perfect. And I'm so glad you said 2 and everything below it. Do you hear how Sam said that? What that implies, and Emma, you're saying no more than 2. You're totally right. That's another way of saying that. At most 2, no more than 2. That implies that 2 is a maximum number, but we also have to take into account every value below that. So 0 children, 1 child, and 2 children. Does that make sense? At most 2 and everything below it. Thank you, Sam. So we want to write a statement that indicates what this probability means. So when you are saying determine the probability that at most 2 will inherit the gene, what that implies is you're going to use the table. We have a probability distribution. We want to know the probability of having 0, 1, or 2 with that particular outcome. So we're looking at just these 3 rows right here. We're just looking at those 3 rows. Now I'm going to write the probability statement so that you're familiar with this. The probability that our random variable, the number of children, will be at most 2. Notice how I wrote this out. X is less than or equal to 2 because we're including 2. That's going to be found by taking the sum of each of those probabilities. So the probability when X is 0 plus the probability when X is 1 plus the probability when X is 2. So I wanted you to see what this equation would look like in general form before we actually plugged in the values. That way, when you go back to your notes, you know exactly what I did and how I got this. So the probability that at most 2 children will inherit the X-linked genetic disorder, we're going to take that 0.0625. Notice I'm not multiplying it by anything this time. I just want to add up probabilities. I'm not finding the expected value. We add the probability that there's only 1 child, that's 0.2500, and the probability that there are 2 children with the gene, 0.3750. Go ahead and add those 3 values up and share that with the group when you have your result. Now remember, we're finding probability, the likelihood that this will happen. Sometimes it helps to say it in a different way. What is the likelihood that at most 2 children will inherit that genetic disorder? And when you have your probability, go ahead and share that with everyone, either through the chat or out loud.
Should we round it?
No, I would like 4 places after the decimal.
Okay.
Yes, Surujni, Donna, Grace, Sam, Lucy's like that one. Lainey, Mallory, excellent. Yes, so we're getting 0.6875. 0.6875. We're going to write a statement that tells us what that means. Thank you, Anthony. Now, there's a so what this means, there's a couple ways of writing this. You can say there's a probability of 0.6875 that at most 2 children will inherit the X-linked disorder. But what I want to do is I actually personally, I would like to convert that decimal into a percentage. Because I think sometimes when we convert to percentages, it becomes a lot clearer what's happening. So I'm going to write the following. There is now remember, if you want to convert a decimal to a percentage, you simply move the decimal 2 places to the right, which is the same as multiplying by 100. So there is a 68.75% chance. You see how we turn this into a percentage and now it's kind of clear what's happening. There is a 68.75% chance that, and now I use the language from the problem, that at most 2 children, finish this statement for me, anyone?
I'll do it.
Yes.
Never mind. I don't want to get it wrong.
No, just try it. And honestly, it doesn't matter. It doesn't matter. Just go for it. Who cares, right? So Monday morning, we're having a good time.
Oh, I don't want to get it wrong. I'm sorry.
That's okay.
Right, so at most, so there's a 68.75% chance that at most 2 children will inherit the X-linked genetic disorder.
Perfection. Wow, I can't type. Look at what I can't write. I'm like trying to squeeze this in there. I almost wrote another E. Will inherit, I can do it, the X-linked genetic disorder. Yeah, that's perfect. That's perfect. Beautiful. Okay. There's a 68.75% chance that at most 2 children will inherit the X-linked genetic disorder. Good. It completes the picture. What questions do you have for me on practice number 4 so far? And I said so far because we got another part. Turn the page. You're going to have to flip back and forth. Turn the page and take a look at part C. Determine the probability that at least 3 children, this is interesting, the probability that at least 3 children. So Sam already told us, and Emma as well, what it meant to be at most 2. So would someone else explain, what does at least 3 mean? Lucy, beautiful. So Lucy says that at least 3 means 3 or more. So I'm going to write this down. At least 3. That's going to imply 3 or more. In this case, it's not like we're going 3, 4, 5, 6, 7, 8, 9, 10. If you look at the previous page, you'll see that we only have up to 4. So we want 3 or more. So we're looking at these 2 rows this time. I'm going to write that down. At least 3 means 3 children or 4 children. I want you to take a moment, write out the probability statement, just like we did in the previous problem. You may have to flip back if you need to. Flip back, write out the probability statement, and find that probability. When you have it, share it privately in the chat with me. I'm going to pause the recording and take attendance while you're doing this. All right, perfect. So we have the probability of at least 3. That means 3 or more, right? So the probability that our random variable takes on values that are greater than or equal to 3, it's going to be the same as finding the probability when the random variable equals 3 plus when the random variable equals 4. So we notice that the probability when 3 children are linked to inherit the linked genetic disorder, that's 0.2500. 4 children, that's 0.0625. Again, this is based on our previous probability distribution, the chart on the previous page. You combine those and you get 0.3125. So we could make what statement? What statement did you write? I would love to hear it.
So there is a
Can I try?
probability. Go
Um,
ahead.
Oh,
No, you can go. Sorry.
No, go right ahead.
Okay.
yeah, go for it.
So I said that there is a 31.25% chance that at least or more than 3 children will inherit the X-linked genetic disorder.
Yes. Perfect. I'm just catching up. Beautiful. Inherit, this time I spell it right. The X-linked genetic disorder. Perfection. Donna, thank you so much. And Jenny, thank you so much as well. Beautiful. There's a 31.25% chance that at least 3 children will inherit the X-linked genetic disorder. Boom, you're done. Excellent. Time for a breakout room. Yes, I like when you guys can work together to make sure that you're understanding this. Plus, I really do feel like it helps to make sure that everyone's on the same page. I'm going to have 4 participants per room, and I would like you to do all of practice 5 together. All right, I'm going to just give you a few minutes. Once you're done, please come back. But if a few minutes passes by, I will just close the breakout rooms. So here we go. And go ahead and join your rooms. I'll see you in a few minutes. All right, welcome back from your breakout rooms. Let's take a look at the problem. I did write down the solution, so I'll walk through exactly how I processed. The only thing is I left part C blank because I want to show you something very interesting. Let's switch over. So for part A, you should have had that the probability that a baseball player will have at most 3 hits is 0.9657. Your company could have been something like, there is a 96.57% chance that a baseball player will have at most 3 hits in a game. Okay. Beautiful. Success on part A? Beautiful. Part B, you should have had a probability of 0.3673. There's a 36.73% chance that a baseball player will have at least 2 hits in a game. Consider 2 or more, right? I'm going to skip part C for a moment and move to part D. And don't mind my little cross out here. For part D, we wanted the probability of 1 or 2 hits. So you simply say, well, what's the probability of 1 hit? What's the probability of 2 hits? And you add those together for a probability of 0.7385. So there's a 73.85% chance that a baseball player will have 1 or more 2 hits in a game. Okay, that was cool. I figured those were not too shabby, right? Okay. How did you answer part C?
Use A and add the 4th column. Use everything in part A and add the 4th column. That's what I did.
Ooh, clever. Very clever. I did not expect that. So we know the probability of at most 3 hits, that's 0, 1, 2, 3. Well, the probability that a baseball player will have no more than 4 also includes the 4th probability. So Surajini is like, I'm not going to freaking reinvent the wheel here. I'm going to take what I got in part A, which is 0.9657, and I'm going to tack on 1 more probability. That's the probability of hitting, of getting 4 hits in a game. Yeah, I love it. Super clever. Next strategy. What else did you, Sam? Whoa, okay. So what Sam typed into the chat was exactly what I wanted to share. Surajini, that perspective of saying, I already did the bulk of the work, let's just tack on 1 more, is incredibly clever. I do want to show you that there's another alternative. Sam, any interest in kind of explaining how you knew that?
Because it was the only probability left, so that's the only one you had to take away.
Oh, okay. Do you hear what Sam said? So I don't know if you can see this in the chat, but he wrote 1 minus 0.0081. When we think about this, we could say to ourselves, well, if I want to find the probability that the baseball player will have no more than 4 hits, that means I'm going to add up the probability of 0, 1, 2, 3, 4 hits. What if that said 48? Are you going to go through and do 0, 1, 2, 3, all the way to freaking number 48? You're going to hate life. Okay, you're probably going to hate life if you had to do that. So I want to teach you a strategy that you can employ that might be super, super helpful. Notice in this case, for our probability. Oh, hold on. I got to mute you guys. Something happened.
Think of it.
Now my dogs just went nuts. That's okay. So instead of adding all of these probabilities together, we can think of it this way. Now, just watch the screen for a moment. I don't want to freak you out, so I want to really break it down in a way that makes sense. Probability adds up to 1, right? So if you added all of these probabilities, you would see that they add up to 1. Okay, that's fine. Now, keep in mind, if we want to know the probabilities combined from 0 to 4, that's exactly the same as saying, well, if I know these 4, I can add them up. That's great. But what if I just take away this remaining probability? Because this one's not in my calculation. So if total probability is 1, why not just subtract this 0.0081 and that'll give me the rest without me even having to add all of those. It's this idea where, let's say you had 50 values in your probability distribution. I want you to just visualize that massive table, 50 values in your probability distribution. If you wanted no more than 48, you're not going to want to add 0 to 48. You're going to want to add, you're going to want to take total probability, which is 1, and you're going to want to subtract the 49 and the 50. the probability of 49 and 50, because that's going to be so much easier than adding all of the probabilities from 0 to 48. So I wanted to give you a little bit of strategy in that regard. So I'm going to write here that the probability that a baseball player will have no more than 4 hits is the same as 1 minus the probability of the value that's left over when a baseball player hits 5 hits in a game. So we have 1 minus 0.0081, and we get 0.9919. Even if you added 0 hits, 1 hit, 2 hits, 3 hits, 4 hits, you got 0.9919. Sam and I just did it in a fraction of the time. I want you to keep this in your mind, because what if you have a massive probability distribution? I don't want you to add all of those tiny values together. I want you to think in a clever way. Think about what's left over. Subtract that from 1. That will get you to your answer so much quicker. Okay? And of course, that's right. There is a 99.19% chance that a baseball player will have no more than 4 hits in a game. What questions do you have for me on this idea? Was that okay? Did I explain that all right? Sweet. Okay, very cool. I love it. We are officially done with that first section on discrete probability distributions. Stephanie,
Could you go back for a second?
yeah, sure. Right here?
Yeah.
Perfect. Did you have any question for me?
No, sorry I came in late. My parents thought it was Columbus Day. I had off.
Oh, yeah, we MCC won't close again until Veterans Day.
How
So,
come some professors gave off?
I don't know. I mean, I'm down for,
Maybe they're just feeling lazy. I don't know.
down for celebrating Indigenous Peoples Day, but that's about it. So yeah, no, the college is open. So if they chose to do it, then that's just something that they decided to do. Cool. Beautiful.
Okay.
All right. Thank you, Stephanie. So we are moving on.
Question.
Oh, yes.
So have you graded the Unit 3 application assignment?
No, not yet. I still
Okay,
have
I
2
was
more turns
just
left.
getting nervous that it didn't upload. I was like, oh my God, I totally did it.
I'll double check to make sure that it did upload. One of
Okay.
the things I do want to point out is you can't upload multiple pages. I will tell you that. So if you want to upload a particular project, it's got to be all the pages in one PDF, and then that's going to be uploaded. And actually, I'm glad that you had mentioned that, because that's huge. So let's say you're like, I had 3 pages for my project and you upload each page, it's only going to save the last one.
Okay.
They have to
So
be.
like if I sent it in Word, it doesn't include the 3 pages, it only includes 1?
No, if you sent it as a Word document, which
I
by
did.
the way, you would just want to save as a PDF, it'll just take 5 pages and make it 1. That's fine. That works.
Okay.
Wait, you said it only saves the last page?
Yeah, if you're trying to upload multiple uploads, it's only going to keep 1. So, and that's the
okay.
last one.
I thought you meant like if you I submitted a PDF with like 2 pages, I think, and I thought you meant.
Perfect.
Okay.
Yeah,
Okay.
yeah, it does. The PDF itself can have like 10 pages as long as it's 1 PDF.
Okay.
Perfect. And that's good. I wanted to make sure I commented on that, because I think a couple of us were trying to upload pages of it and it didn't. It's got to be 1 document, like 1 complete document.
Okay. I got scared for a second. And I was like,
And I will grade those soon, but I can also double check. to make sure that it uploaded correctly and I have your entire document. Okay, which is probably what, 2 pages, I would think, for everybody, about 2 pages.
2 pages.
Okay, perfect. All right, let's go over to the notes. And we are ready to start talking about binomial probability distribution. When you see the word binomial, how many outcomes do you think we're referring to? Binomial, how many outcomes?
2.
Yes,
Yep.
exactly 2. So what I'd like us to consider when we see binomial distributions is this first statement is going to be really, really helpful to us. Angelica, would you read this statement out loud to everyone about the binomial probability distribution?
Many experiments are composed of repeated trials whose outcomes can be classified as either success or failure. Such experiments are called binomial probability experiments. Think either yes or no, or pass or fail.
Perfect. Okay. Think either it happens or it doesn't. And if that's a scenario where either it happens or it doesn't, binomial probability distribution. 2 outcomes, either it does or it doesn't. Let's play a quick game. You may need your calculators. If there is a 32% chance that something does happen, what's the likelihood that it doesn't?
68% chance.
68% chance. We know that if there's a 32% chance it doesn't, that there's a 68% chance that it does. Let's play another one. What if I tell you that there is a 3% chance that something does not happen? What is the likelihood that it does?
0.97.
97% chance, right? So we are capable of doing this no problem because we know that probability is out of 100% or total probability of 1. I want you to keep that in your minds as we move through the binomial probability distribution. I think if you really just kind of accept that piece right there, this actually is going to go really, really well for you. Now, I will tell you there is a fancy formula for this. So your cell phone calculators will not be able to calculate what we're going to have to do. So if you're using a cell phone, you're going to have to put it away because it's not going to be helpful at all. You're actually going to want to end up throwing it against the wall. And I don't want you to do that because I want you to have a cell phone. So make sure you have your real calculators, real ones, your scientific calculators. The other thing you can use if you don't have this handy right now is, believe it or not, Google. Google is a great resource for doing those calculations as well. Let me show you what I mean. And I think you'll see very quickly that, oh, I cannot use my cell phone for this. I don't have the capability. Okay.
You can also go in Desmos. There's a free calculator on there.
Yes, Desmos will work too. Or Wolfram Alpha. Wolfram Alpha is pretty cool. I actually use that at RIT a lot. Ho, would you read the binomial probability experiment and read statement A and then the sub-statement I?
One more, please. Was it?
So right here.
Okay. I think I'm just gonna read off the screen.
Yeah, sure.
The binomial probability distribution.
Oh, I want you to read this one right here.
Okay, sorry about that. Yeah.
That's okay.
Binomial probability experiment. An experiment that is made up of repeated trials that possess the following properties.
And go ahead and just read part I, just the first one.
There are n repeated identical independent trials. Independent trials mean the occurrence or non-occurrence of one gives no information about the likelihood of the occurrence of the other. Another way of stating this is the probability of event A is unaffected by knowledge that a second event B has occurred or has not occurred.
Yes, that is very interesting. So we're looking at independent trials. So there's no influence if one occurs or doesn't occur. It doesn't matter. It either is or it isn't. It's not a big deal. Thank you, Hope. Lucy, would you read parts 2, 3, and 4? Tell us more about this binomial probability experiment?
Each trial has two possible outcomes, success or failure. And then it says P success equals P, and then P failure equals a backwards P.
No, Q, and we use lowercase letters P and Q to represent probability of success, lowercase p, probability of failure, lowercase q. Keep going.
And P plus lowercase q equals 1.
Yes. And last statement.
The binomial random variable X is the count of the number of successful trials that occur. X may take on any integer value from 0 to n. Recall that n is the total number of elements in a set.
Beautiful. Okay, this one piece about the P's and Q's, it's actually really, really important to know. And if you start to get this down early on, it's going to make your life a lot easier as you look at other distributions in the future. So lowercase p refers to the probability of success. Lowercase q refers to the probability of failure when you're looking at this. Keep in mind that if we know one, we know the other, just like we played that game together. I said if there's a 32% chance that something does happen, you said there's a 68% chance that it doesn't, right? I mean, that's straightforward. If you know one, you know the other. That's what this is saying. We know that the sum of the probability of success and failure is equal to 1 because that's total probability. So again, if you know one, you know the other. Okay, let's continue talking about parts of a binomial experiment by looking at a particular example. So I want to walk you through this, and I'm going to do this slowly because I want to make sure that everything makes sense. So please make sure you are taking notes, you're following along, you're doing all that good stuff, or just observing. Remember, I am going to upload this video anyways. So if you would like to just take a moment and just observe what I'm doing without writing down, that's totally cool too, because you can always look back on the video and then use that to write notes. Example. It is known that 40% of all graduating seniors on campus have taken a statistics class. Did you hear that statement? What does that imply?
60% have not.
Done. Did you hear Angelica say exactly what that implies? If it states that 40% on campus, graduating seniors on campus have taken a stats class, 60% have not. You see? Okay. So that's the first thing I'm going to do. I'm going to underline this statement. So we'll use that in a moment, and I'm going to write out exactly what that means. That way it's very clear. We're then told 5 seniors are selected at random. That's very interesting to note. We're given a value, a total number of seniors that are being selected. That's interesting. And of course, they're going to be asked if they have taken a stats class. So let's fill in the information. N is the total number of elements in your set. We have 5 seniors, so I'm going to write N is 5 seniors. That's the number of elements in my set. Those are the ones I'm going to ask. A success is a graduating senior. I'm just going to abbreviate. A graduating senior who has taken stats. A failure is the opposite. So a failure is a graduating senior who has not taken stats. Now we want to find the probabilities. So we had said there's a 40% chance of all graduating seniors on campus having taken a stats class. How do I write that as a decimal for P?
Four.
0.40.
Yes, so we could write 0.4 or 0.40. I'm comfortable with either way because they both say the same thing, which means we know the probability of failure. Angelica already said it. She says there's a 60% chance that they have not taken a stats class, which means Q must be what's left over, which is 0.60. Now we think about, well, what are all the possible outcomes that can come from this, right? If we're asking 5 seniors, hey, have you taken a stats class? They could say yes or no. And in which case, 0 of them could have taken a stats class. 1 of them could have, 2, 3, 4, or all 5. So when we look at this X value, this random variable, it's based on whether or not they have taken a stats class. And if we're asking 5 seniors, then we can have any number of them saying, yeah, sure, I took a stats class. So these are the possible values that X, our random variable, could take on. I do want to point out we haven't done anything with this information. We're simply setting the stage. So having broken down the binomial distribution in this way, the binomial experiment, what are your thoughts on this setup? Are there questions about any of these values? Okay, let's turn the page. We're ready for a formula. Dun, da, da, ban. Okay, this is a little crazy, no big deal. I swear it's not a big deal. For a binomial experiment, let P represent the probability of a success and Q represent the probability of failure on a single trial. Then P of X, that's how you say it, P of X. Then P of X is a probability that there will be exactly X successes on N trials. So P of X is found by taking N choose X. I literally said N choose, like to choose, items. N choose X times the probability of success raised to that value, the number of successes, times the probability of failure raised to the number of failed outcomes, basically how many people would be failed. So for instance, let me show you what I mean. I'm going to just write an example in here. What if I wanted to find the probability that out of those 5 seniors that we talked to, that only 2 of them said yes? So we want to know what are the chances that that'll happen, right? So we're going to say, let's find the probability that 2 seniors said yes. When we write this N choose X, that means the total number of people we asked and the total number that we are expecting to be a success, right? We're thinking 2 people will be successful. So here, it is not a fraction. It is literally a combination. So you actually write it with the N value at the top and the X value at the bottom. It's just a particular notation for this. So N is a total number of people we talked to, so 5 seniors, and we want to know the likelihood that 2 of them say that yes, they took stats. So we want to do 5 choose any 2. Okay, out of the 5 people, out of the 5 seniors, you want to choose any 2. Is that making sense so far? Next, our formula reads the probability of success. Well, according to our previous page, the probability of success was 0.40. So we're going to write times 0.40. Now remember, notice here that it's raised to the power of X. If we want to know the probability that 2 seniors took stats, then that means each of those 2 will say that yes, they did take stats. So the probability of success for those 2 students. So how many students are going to say no?
3.
Okay, 3. So you take the probability of failure and you say, well, there are going to be 3 of them that say they don't take stats. There is your equation. So we have 5. We're going to choose only 2 of them to say that they've taken stats. The likelihood that they've taken stats is 0.40, but there are 2 of them who are going to say this. But then that means that there are 3 who are going to say, nope, I didn't take stats. That wasn't part of my degree requirement. And we want to calculate this probability. So let me show you how you would do this on your calculators. Okay. So notice here, we have this PRB button. I want to just press it so you can see what's happening. So we have NPR, this is for permutations, and NCR, this is for combinations. So we want to pick the combination. However, before we do this, notice it says N and then the C and then the R. That's the same as N choose X. They just use R instead of X. So what we want to do is we actually want to type in the number 5. Then we're going to press PRB, because remember, I'm just doing this first part, this part that we have probably haven't seen, either we haven't seen before, or we haven't done this in a while. So we press PRB and we're going to choose the combination. N choose R, 5 choose 2. So we have 5 choose 2. Notice where the NCR is, it's in between those two values. And then you find that 5 choose 2 is 10. There are 10 combinations out of those 5 students. I want you to think about taking 5 students from our class and choosing any combination of 2 of them. There's going to be a lot of combos, right? If in my 5 people I had Jenny, Angelica, Sam, Lucy, and Ho, well then there's going to be a bunch of different combinations. Specifically, there's going to be 10. So the calculator found the number of combinations that you could have. When we do this, we then continue through the equation. Notice I have times, so we're going to do times, and we have 0.40 squared. We can press enter if we would like, and then times 0.60 to the 3rd power. And this time I use the caret to show raised to the 3rd power. And then I find the probability. The likelihood that exactly 2 seniors will say that they have taken stats out of the 5 that we asked is 0.3456, or there's a 34.56% chance. That is how we calculate probability for a binomial distribution.
Do you know how to do that on a TI-83? I don't have a PRB button.
You have a math button. Let me grab my other one. Hopefully it still has battery life. Let's see. I have a TI-84 plus. Let's see if this still turns on. Yes, it does. Ooh, the battery is extremely low. Let's see. Let's see if we can do this anyways. If you pick the math button, then you scroll over to probability. You have that as your option number 3 or something similar to that. So let me try doing 5, and then let me choose that. 5, choose 2, and there we have it. So it's the same process. You'll just have to find it in the math button. Does that help?
Yeah, thank you.
Beautiful. You're welcome.
I have a question for the TI Inspire. Can we do that on?
I've actually never used a TI Inspire. Like I've never even touched one in my life, which is kind of crazy.
Oh, for real?
Yeah. Maybe there's some sort of math button, or maybe there's like a probability button that would help, something like that. You know, I'd have to do some investigation online just to see what it looks like.
I have a TI-36X Pro, and I see the NCR, but
Oh, good. So
But
you
no.
want to type in 5, then when you see that NCR, select it, then punch in 2. That should work. Give that a shot. While you're doing that, I also want to show you how you can just type this into Google, which is pretty crazy. Like literally this says 5, choose 2. So I'm just going to type in 5, choose 2, and there it is. It does the math for you, see? And if you wanted to, you can say, well, I want Google to just calculate the entire thing. So I'm going to multiply it by 0.40 raised to the 2nd power, and then 0.60 raised to the 3rd power. And then we punch that and we get 0.3456. And you can see here that it's clearly typed in correctly because it matches exactly what we had on our notes. Okay, so this is another alternative too. Worst case scenario, if you're struggling with finding that on your computer, no big deal. Type it into Google, Google will do it for you. Okay. No
You
big
have to have the star next to that too.
Like the times, no, actually, let me take that times out. Parentheses indicates multiplication, so it automatically knows that it's multiplying, so it doesn't, you don't have to actually type that in.
Oh,
Can you show again where you got the caret sign on Google? I'm sorry, on Google.
Oh, on Google? Oh,
Yeah.
I actually typed in, I held shift and I pressed 6. Look at your keyboards. There's a little caret above the 6. You just hold shift and press 6.
I was trying to do it on my phone. That's why.
Ah, yeah,
I guess this is why you said the phone can't work.
right, exactly. That it ends up being very, very tricky. If
Okay.
you did try to do this on your phone, I would still use some sort of computer software to do the 5 choose 2. But then when you go here, you can simply say, well, let's turn the cell phone to the side. And then you could do 10 times, and then 0.40 is squared. And then you do times 0.60 to the 3rd power. Luckily, it has to the 3rd power there. If it was to the 5th power or whatever, you'd press this X to the Y key, and then you type in the number. So for instance, let's say I wanted to do 2 to the 6th power. So 2 raised to the 6th power equals, nope, that didn't do it. 2 raised to the 6th power. There it is. I just had to clear it. So use the X to the Y button. It's a little harder to see. X to the Y button to raise it. That's why you shouldn't use the cell phone calculator. Don't do it. Don't do it. Don't do it. Don't do it. Okay. Any other questions about the calculators? And I apologize that I have never used the TI Inspire, so I am unsure as to what it looks like on that calculator. Okay. Look at part B. The number of ways that exactly X successes can occur in N trials is represented by the symbol N choose X. You actually can do this by hand. I wouldn't recommend it. I wouldn't recommend it, especially when you have very, very large values. It can be kind of frustrating. So let me just show you an example of what this would look like. 5 choose 2. So if we wanted 5 choose 2, where it says N, we're going to replace it with a 5. So this is 5 factorial over X's are 2, right? So it's 2 factorial. And then N minus X, 5 minus 2, which is 3 factorial. Now, when we say factorial, what we mean is you take the number and you multiply it by all the values, all the whole numbers that are smaller than that one, with the exception of 0. So really you're multiplying it by the counting numbers that are 5 or less. So that's 5 factorial. Think about this exclamation point here. It just kind of means like you expand it. So 5 times 4 times 3 times 2 times 1. 2 factorial is going to be 2 times 1. And then 3 factorial is 3 times 2 times 1. So we could do this by hand. Let me show you what happens when we simplify. Notice here, I see that the 3 divided by 3, that reduces, it leaves us with a 1. 2 divided by 2 leaves us with a 1. Obviously, 1 divided by 1 is still 1. Then also notice we have 5 times 4, we have a 2 times 1. We can reduce, 2 can go into itself once and into 4 twice, and 5 times 2 is 10. So we found that there are 10 outcomes. So we can do this by hand, but I wouldn't recommend it. That would be kind of frustrating if you had really large numbers. Okay, I just wanted to at least show you once, but I did type in here how you would use the NCR key, PBR or PRB, and then go to NCR. Okay. Any questions on that? Okay, hopefully I'm not freaking anybody out. Part C says the probability of exactly X successes is P to the X, of course. The probability that failure will occur on the remaining trials, that's Q raised to the N minus X. You're just saying how many items are left. Those will be considered failures. So it's the probability of failure raised to that number. Advice, find N minus X first. If there are 12 people in your study and 8 of them are successes, then that means 4 of them will be failures, right? Because you have 12 altogether, the probability of success, it will look like this. So it'd be the probability raised to the 8th power because 8 of them are successes. Whereas failure, you're gonna have 4 left in that group. So notice that 8 plus 4 is 12. So out of the 12 people, you need to assign them a value. They're either a success or a failure. You have to assign them a value. We have enough time to try a problem together. Let's look at practice number 6. All right. Stephanie, would you read practice number 6?
Sure. According to the recent study, 65% of all homes in certain country have a high level of random gas leaking into their basement. 4 homes are selected at random and tested for random.
I think it's either radon or radon.
It's right on.
Thank you.
The random variable X is the number of homes with high level of radon.
Radon.
Yeah,
Yeah, perfect.
out of the 4.
Aha, okay. First things first, are there N repeated independent trials? How many trials are there? How many total trials? Yes, yes, 4. So we're gonna say yes. We're gonna say that N is equal to 4. There are 4 trials here. Notice you don't see it really until the very end, out of 4. The number of homes with high levels of radon out of 4. Very, very nice. Are there 2 possible outcomes? So someone other than Leah and Stephanie, are there 2 possible outcomes and what are they?
If it does have high levels of radon or if it doesn't.
Perfect. So yes, it does. And the first outcome is, do they have radon leakage? Or not? Is it okay if I just wrote it that way? I know that's completely informal, but I figure these are our notes, so it's fine. So does the house have radon leakage or not? Okay. All right, so what is the probability that they do have radon gas leaking into their basements? What's the value of P?
0.65.
Yes, the value of P is 0.65. We know this because it says 65% of all homes in a certain county have high levels of radon gas leaking into their basement. So what's Q?
0.35.
Yes, beautiful. This is kind of nice, right? Okay, now that we have our verification, let's answer the following based on our given info above. So what is the probability that exactly 2 houses were found to have a radon gas leakage? So we want the probability of exactly 2. So we want the probability of X equals 2. No worries, Mallory. So we are going to use a formula, N choose X. We know that, you know what, I'm going to write the formula here because I think that might be helpful. So the probability that X is equal to a specific number of values, right, is going to be N choose X times the probability of that many successes times the probability of that many failures. So there's your formula. That way you have it. And again, it's going to be helpful to talk through it as you do it. We had 4 total houses, so that's N. And we want exactly 2 of them to have radon gas leakage. We don't want them to have it. We want to find the probability that that is the case. So that means When we say how many have radon gas leakage, we're saying 2 of them. So the probability of success, 0.65, you raise that to the second power. Well, if 2 of them have gas leakage, then the other 2 won't. So the probability of failure is 0.35, and we'll say that those 2 do not out of the 4 houses. Any questions on that? Cool. Let's go ahead and punch this into our calculators. So for PRB, choose 2. If you punch this in for choose 2, you should get 6 as an answer. There are 6 possible combinations. Multiply it by 0.65 squared, multiply that by 0.35 squared, and you should get the following decimal. Verify this with your own calculations.
So when you do 4, choose 2, you get 6, right?
Yes, absolutely. That's exactly correct. Good. I'm going to just take into account 4 values after the decimal. I don't have to round up at all. I leave it as 0.3105. So there is a 31.05% chance that exactly 2 houses have radon gas leakage. And that's how you find probability using the binomial probability distribution. All right, everyone, I will stop here. Excellent work. We will continue looking at binomial distributions on Wednesday, including using a fancy schmancy table. Excellent work, everyone. I will see you all Wednesday.